So in our notes here about generalized linear models, or GLM, we discussed one of the components is the link function. Up until this point, we've only covered one possible link function for our binary options of the logit. Now first, a little refresher of what we mean by binary. Our data that we are working with, we would refer to as success-failure data, or it's considered binary because there's only two options. When we looked at our data, for example, we have a whole bunch of zeros to represent failures and ones to represent successes. So since we only have two options, that's just what we refer to by a binary. So because of that kind of data, there are going to be certain types of link functions that one might be interested in. One reason we really liked the logit link function was that it bounded values between 0 and 1. And since we were trying to estimate a probability of success, that made perfectly good sense that I wanted my values then to be between 0 and 1. So there are other link functions though that we could use besides the logit. One function that we're going to talk about is being used to create a link function is called a CDF. Now some of you that have taken Stat 250 or higher for the calc-based classes have probably talked about a CDF. But again, that's not assumed knowledge, so let's talk about what a CDF or a cumulative distribution function is. So first, notation-wise, we generally use the capital F of x to represent a CDF. And what it represents is it's the probability that big X is less than or equal to little x. Now, knowing the definition of a CDF is not what is important for our class. What is important is realizing what this P is standing for. This P represents it's a probability. So that is, if I were to use a CDF, I know that this must be between 0 and 1. In order to understand a CDF a little bit better, we're going to talk about a function that likely none of you have ever seen before, and due to its name, gets used a lot in these types of notes. It's called the Logistic Distribution. For those that are interested, this is its corresponding PDF, because that's what little f represents here. This is our PDF. And so it has two different parameters in it, our mu and our sigma. And if I change those two values, that's going to change what my function looks like. At the top of the next page, I gave a graph of what the logistic PDF would look like if mu was equal to -2 and sigma was equal to +2. My line was very light here, so I tried to trace it over so we could see it a little bit better, even though it's not perfect, of what it looks like. Now what we'll see is this looks a lot like a normal distribution. It is different, so be a little careful of that. But right, we have this idea of the symmetric looking picture that we're working with here. It's actually centered at mu, which is our -2, so that's why it's shifted over here a little bit as well. But what I really want us to see from this PDF is actually what the CDF looks like. And so a CDF is no longer just plugging in a value into that PDF, it's now looking at cumulative probability. So imagine for those that have not done a CDF before, as I'm kind of tracing this line, I'm going to gain probability each time I go. And so I'm getting more and more and more area. So imagine that the CDF is representing how much area is to that value or to the left of it, right? So I'm going to continually gain more and more area every time I move to the right here. So our CDF is bounded between that 0 and will go no higher than 1. And if we look at this curve, this also looks pretty similar to our model that we fitted using the logit line, but it's going to be a little bit different. So although it has that shape that I'm used to seeing, it's not going to be exactly the same. It could be a little bit different. Now, how we're actually going to use the idea of a CDF is another link function that we're going to discuss is called the Probit Link function. So this is going to be our function that uses a CDF to help us find it. So more specifically, it's going to be using the normal distribution, the one that we are used to, that Z distribution. Now, if you remember from your first class involving the Z table, there were numbers on the inside and outside of that table. So for example, here I've pulled up my normal table that I use. Remember, there were kind of two different kinds of values. There was the outside value of the z-score, then there was the inside value of the actual probability. So we're going to be using these same two types of ideas to understand how to use this Probit Link function. When you see this capital phi inverse, this is the Greek letter phi inverse, so just to the negative first, so that'd be called inverse. This is when you're working backwards in the normal table. Or in a sense, what you're trying to find then is you're finding the z value. So you're finding the value here on the outside of the table. Versus on the inside of this table is where probabilities live. And that's what this pi is going to represent, is then that probability. So going back to what we've discussed so far about generalized linear models, you'll recall that there was the systematic part of the equation. So let me scroll back there real quick. So in this systematic part, this is when we had the alphas going on there, plus the slopes times our explanatory variables. Again, right now we're just using one explanatory variable. So if I have just one explanatory variable, this is going to translate to just alpha plus beta x. So then when I look here at my Probit Link function, here's that alpha plus beta x. So this is how we're looking at the systematic component. But our ultimate goal is to go back here to our probability, because that's what we're trying to model. That's our random part that we're trying to model. So we're actually going to want to find the probability. And so what you'll notice here symbol-wise is that it uses the regular phi versus here is the phi inverse. So phi is kind of going to the table, figuring out which row and which column you are at and arriving at a number here in the middle, versus that phi inverse is I'm starting with a number here in the middle and then working out to find the row in the column that I'm working with. Okay, I hope that makes some sense with the table, and we'll get to use the table in our example here shortly as well. Another link function that often gets used for binary data is the complementary Cloglog Link function. And again, first as a reminder, all these logs that you see me doing, we're still talking about natural log. And so let's sort of write this out in that way if that's more helpful here for you. So if I take the natural log of the negative natural log of 1 minus my pi of x, we're going to get alpha plus beta x. So this is where I take complementary log pieces of it. The complement of pi is the 1 minus pi. So complement's just in a sense the opposite here, or a probability of failure. So that's where the complement part of the name comes from. And the log is the fact that there's two logs in here, even though one of them is technically negative. So that's just how it's getting its name. But then again, my ultimate goal here is to actually solve this for pi. So if I want to find pi, which you could do the math to get it here as well, it's going to be 1 minus e raised to the negative e alpha plus beta xi. Now this one was a little bit harder for me to write out a nice formula that you could see, so let me write that one out as well. So that's going to be 1 minus e to the negative e to the alpha plus beta x. That's what it would look like if I wanted to write that out a little bit nicer looking. So these are going to be the three link functions that we're going to talk about. So let's start by looking at a graph of these three different link functions. So we're going to call them the logit, the probit, and then I call it the cloglog for the complementary log. But for this example, just to see how they're similar but different, we're going to be using the same alpha and beta. So for our example here, alpha is going to be equal to 1, and then beta is going to be equal to 1/2. And so if I use those in each of my 3 different link functions, using that alpha and beta in each of them and then transforming them back to get my pi, here's what my graphs would look like. So the red represents the logit. Now you can't see this as well as I wish you could here. And then the blue represents the probit. So there's a little blue dashes there. And then the green dashes and dots is the complementary log one. So what we can kind of see is how they are all similar and have this S-shaped looking curve, but they do it slightly differently as well. So we want to make sure we talk about how they're similar versus how they are different. But then just for comparison, right, I want to be able to have both a positive and a negative trend. So let's look at them on the other side here. Same colors representing the same different link functions. All I've done now is change my beta to be a negative 0.5. Remember, beta is like our slope parameter telling me how the probability of success changes as x gets bigger. So we are still able to model that negative relationship as well. What I've given you here is just some of the code for one of those plots. For those that are interested in it, we're going to be doing other plots later, but for those interested in it, let's talk through a little bit of this code. So first I'm just setting my alpha and my beta. And then I'm kind of writing out the different logit, probit, and complementary log functions. Now it's been a little while since we looked at the logit. So recall for the logit, when I wanted to find my pi hat of x, we had e to that alpha hat plus beta hat x over the 1 plus e to the alpha hat plus beta hat x. So that's what I'm, in a sense, typing out here, except for right now I know truly alpha and beta, so they don't have the hats on them. So that's what that pi logit is doing. Now for the pi probit, keep in mind first that we're trying to do it in terms of pi. So for the probit, I'm going to be actually trying to find the probability from my normal distribution of whatever alpha plus beta x is. So that's why I'm using the p norm function, because that's going to give me a probability from the normal distribution. And I literally want it of alpha plus beta times x. To be more specific, even though it's the default for the p norm function, I'm specifying that it's going to be a mean of 0 and a standard deviation of 1, because this is what allows me to get a z distribution to be working with here. So the probit one is then doing phi of alpha plus beta x. And finally, to get the pi for my complementary log, as I've written it out here, it has to be 1 minus e to the negative e to the alpha plus beta x. So that's just what I'm typing out here. That's 1 minus e raised to the negative e of alpha plus beta times x. Then I'm just putting all of the values, my values of x, pi logit, pi probit, and my pi complementary log. I already had x specified in a previous example, so that's why I'm not having to actually redefine x here. So I'll show you that when we pull up the R code directly, so you can see that it was already defined. And then for this PAR, it's going to give me my plotting area, so I'm going to do a square. It's just what the S stands for. And then this is going to be my plot. For my x's, I just literally want to use my x's. So it's inside that plot.data2, and I'm going to pull off the x variable. And then for my y, I'm going to represent the pi.logit is the one I'm going to start with. I technically could do any of the ones I wanted. Just labeling things here, setting bounds of 0 and 1 for my y. For my type here, just using the 1. The color is going to be red, and then title on the plot. So let's actually just run that part of my code here first. So first, recall in my code up here is where I already have my x defined, so that's why I do not need to recode that here in my new code that I'm working with. Otherwise, I would have had to specify it. Here's just running my alpha and my beta. Now here's getting the logit, the probit, and the complementary log values so that I can actually use them to plot. Putting all of that data into one data set. So again, if I want to, you could always pull up that data set to look at. So inside of it, we have our values of x, our pi, our for logit, probit, and complementary log. Then I'm going to get my plotting here of a square. And now actually do my plot. So here's the first plot. This is going to be the logit. Getting a solid line by using that line type of 1 here for that. Then after I've run the plot function, the lines function will allow me to put a new line on the exact same plot that I was working with. So that's why I'm using the lines function and not the plot function again. This next one, notice I'm using the same values of x. All I'm changing is I'm using the probit instead of the logit pi's. I'm changing the color as well as the type. So we can kind of see a little bit different there as well. So now there's my probit function on there. And then finally, same idea with the complementary log, just changing colors and a little bit of the line type so it looks a little bit different. So there's all 3 of my link functions plotted for the same alpha and beta. Finally, the last thing I'm doing, that if you look at our plot that I currently do not have there already, is the label or our legend that we would like to have with it. So this is where I'm doing just creating that legend that I put on there. So the 3 labels I'm going to use are logit, probit, and cloglog. So I'm just defining what names I'm going to use inside my legend. And then for it's just a legend function, it's going to put a legend on whatever plot you currently already have up. This locator 1 will actually not already put the legend on there for me, but will instead let me click to where I want to see the legend. So we'll see that here in a moment. For the legend, I'm going to use the names that I just defined here above. For my line types, notice I'm going to match what I had up here. So the type here was 1, type here was 2, and then type 2 here, and the type 4 there. So I'm just making sure I have those same lines in my legend as well. And then my colors in the same order. So I did logit, probit, complementary log. So logit was red, probit was blue, and the complementary log was green. The BTY just stands for box type, and so N just means I'm going to put no box around it. So now if I run those 2 lines, you'll actually notice that it's not done anything. And you'll now notice this little stop thing has ranged up there because it's sort of waiting for me to do something. So I'm just going to go over here and click, and it'll put my legend on there for me. If you end up putting it in the wrong spot, you can just go back all the way up here, rerun your entire plot, and click a different place to put it to make sure it looks good for you. So that's just what the plot looks like and a little bit of the code of how we got there. All right, next let's talk through a few notes about comparing these different link functions. So our first note is looking at the logit and the probit. So the logit and the probit actually intersect when pi is 0.5. So I go back up here and look at my graph where pi is about 0.5. That's where that blue and red line are going to cross. And that's going to always be true for the same alpha and beta. So do notice that here I use the same alpha and beta. There are times that you're not going to probably get the same alpha and beta when we're actually fitting data. So here I force them all to have the same alpha and beta. So this is going to be true when they have the same alpha and beta. Both of the logit and probit are also symmetric. The complementary log-log is not. Now again, what we mean by symmetric is if I took like a piece of this logit, kind of flipped it at 180 degrees, it's going to lie on that other half of it. You'll actually pretty easily be able to see that's not true here for the complementary log-log, because it actually stays here at 1 or pretty darn close to it quite easily, and takes a little bit longer to drop off of 0. So you'll notice that this little tail down here for the green isn't near as long as the one is up here. So this is what we meant by symmetric. Even though it still has that same pattern, I couldn't take this half and lie it on the other one because this would be longer, for example, in this one. All right, a very important note that I really want to make sure makes sense. When we fit data, so when we fit these link functions to the data, we will not expect our alpha hat and beta hat estimates that we get to be the same. So that is when I'm going to go through and actually run a different link function. I'm going to use the probit or the complementary log-log instead of the logit. I am more than likely going to get different estimates for alpha hat and beta hat. So the estimates I got here for alpha hat and beta hat, when I fit the probit to my data, does not mean I'm going to get the same values there as well. So I don't want you freaking out if that doesn't happen, because more than likely it's not going to happen. Very seldom actually will they end up being equal to each other. What you'll see next is talking about which model or link function should we use. And I think it'll make more sense to discuss those after we actually fit all of the models in R and look at the different outputs, which we're going to do in the next video. So the next video is going to focus a lot on R first, so just making sure we feel good in reading the code as well as the output that we get, and understanding how I can use that output to help me figure out which model I should use.